or Roca, who is a senior at Manhattan College. She's going to Michigan State University in the fall for a PhD program in computational mathematics, science, and engineering. And she'll talk to us today about ranked choice voting. Thank you very much for joining us.
Hi, thank you so much for having me. I'm excited to be here and I'm looking forward to giving this talk, and everything I've seen so far has been amazing. So this has been a great day. For those of you who have been here in the morning and saw Dr. John Hodge's talk, so this is now delving into one of those projects. So this work on ranked choice voting and random sample voting was done in the 2019 summer Grand Valley State University Math RU with myself, my partner, Caitlin Patel, who's at Rollins College, and then of course, Dr. Hodge. Okay. This is being annoying. Okay, so just a quick overview of the next 20 minutes or so. So my goal is just to highlight how complex and not straightforward voting can be, and the necessity of understanding and exploring these different types of processes and voting methods, and the ways in which math can make meaningful contributions in these areas. And so the first thing I'm going to do is just go through some different voting methods. I know we've seen some examples gone through in the past presentation, but so I'm just going to lay out a few, and then all of these will help inform us for the work we did with random sample voting, and kind of looking at random sample voting as a way of solving the issue of informational barriers that inherently come with ranked voting systems. Okay, so I don't know, I think there's a non-zero probability. You can assume that maybe sometime the Institute of Mathematics and Democracy will have an election. And so let's imagine that scenario where we have 4 candidates running: Felice, Gerald, Helen, and Ivan. And so we asked all of our voters, though, to rank the candidates. And so here is just what our the electorate gave us. So we can read this by saying that 12 voters ranked Felice first, then Gerald, then Helen, then Ivan. 7 like Gerald the best, then Helen, then Ivan, then Felice, and so on and so forth. And so the natural question is, okay, we have our ballots, but now who should win? So there's a few different ways we can go about looking at this, right? And so I think the method we're all most familiar with, at least in our voting experiences, is plurality, right? Where everyone votes for their favorite candidate and the person with the most votes is declared the winner. So here in our ranked system, we'll only be looking at that first row. And so we see that Felice has the most amount of first choice votes. And so that means that Felice will win. So it's worth noting that this plurality system doesn't necessarily guarantee a majority. And we see this in a lot of different examples, including in Maine, and I'll be talking about Maine a lot, with the 2010 election for the governor, where Paul LePage won with only 38.2% of the vote. So we can see how this isn't necessarily desirable from everyone, especially because if we look at if we look more closely at our rankings, we have 15 people who didn't vote for Felice, and in fact, they voted her very low, right? No one ranked her in their second choice. She's the last choice or the third choice. So is there a better way to do this? So perhaps we consider instant runoff voting or ranked choice voting. And so the way this works is that we look at the first choice and we see if anyone has a majority. If they don't, then we're going to eliminate the candidate with the least amount of first choice votes and then transfer their votes in the next ranking. So here we see Ivan has the fewest first choice votes, first place votes, with only 3. So he's eliminated, and now his votes are going to be transferred to Helen. So now we have 12 votes for Felice, 7 votes for Gerald, and 8 votes for Helen. This means Gerald's going to be eliminated next. Now it's between Felice and Felice and Helen. And so we see Helen, this adds up to 15 as opposed to Felice's 12, and so Helen wins. One thing to note is that the nice thing about instant runoff is that this only happens in one election. So we can think about one, prominent area recently was with like the Georgia elections, right? And so the election day in November didn't lead to a result for the Senate that was a majority. And so there was another election in January. And, there was a lot of news about that. And so here there's no 2 election days. Everything is done up front. Okay. So we could also look at the board account, which I know is just talked about. And so we're going to just assign points based on the ranking of each candidate from the voters. And so here we'll say that first place is 3 points, second place is 2 points, third place is 1 point, and last place is 0 points. There are different ways to scale this. You might want to give the last place 1 point. Giving 0 points would like effectively nullify that last vote. So there's different ways to do it, but either way, we're assigning points and seeing what happens. So let's do that. It's worth noting that the board account is not really used in politics. It is used in sports. I am not a sports person, so we'll just move on. Okay, so if we look at Felice's border score, she'll get 3 points from those 12 voters. She'll get 1 point for being in ranked 3rd place from 5 voters, and she'll get nothing from those 10 voters who put her in last place. So when we calculate that up, she gets 41 points. We can continue doing that with everyone else. So Gerald will have 3 times 7 for his first ranking, 12 times 2, then 1 times 3, and then he gets nothing for that last. So Gerald now has 48 points. Helen, when we do it, will get 47 points, and Ivan gets 26. So he's kind of behind. So when we look at all of these voting methods together, so we see that Gerald would win here, right? He has 48 points, which is the highest. So when we look at all of these things together, we see that Felice wins under plurality, Helen wins under instant runoff, and Gerald wins under the border count. So 3 voting methods that are used, right? They seem valid, 3 completely different answers. And then poor Ivan doesn't really get much regardless. But maybe Ivan wants to look at a head-to-head contest because something interesting happens here. So if we look at just 2 candidates, so let's look first at Gerald and Helen, we see that Gerald would win because he has the 12, 7, that's 19, as opposed to the 8. So Gerald would win against Helen, but Felice would beat Gerald if we just look at those 2, right? So we have 12 to 17 to 10. But Ivan manages to beat Felice, right? From by 15 to 12 from all of these. And so we see that if we follow this logic, if Ivan's better than Felice, who did better than Gerald, who did better than Helen, then we have Ivan as the winner. So naturally, the other 3 are not thrilled about that. And so let's say if Helen decides that she wants a rematch, Helen easily wins in a landslide from 21 to 3. So what we notice is this peculiar scenario happening called a preference cycle, where we see that when we're doing these head-to-head competitions, that at least the majority, no one's satisfied because everyone can just keep calling rematches and come up with a way that they would win. So no one's happy. And I think this is just a really good illustration of how complicated that voting methods are, and there isn't really one clear way forward. Okay, so this was a great example, but I have a lot of non-math major friends, and so a question I get asked a lot is, but does this actually happen in the real world, and like, should we care? We can construct this, but like, what's the point? And so the answer is yes, this does happen. And there's a really cool example from Maine again, this time in 2018, not 2010, where the first congressional election was held using instant runoff voting. And we noticed that in the second congressional district, using instant runoff voting actually made a difference. So in that summer of 2019, I spent quite a lot of time looking at all of this data because of this difference. There was quite the controversy that was caused. There was a lawsuit started. But the nice thing that came of it was that Maine published all these results. So all the ballots. So I spent a lot of time combing through these raw ballots and trying to analyze them and see what we can use. So let's look at the official finalized data. So we see that the Republican candidate, Paula Quinn, had the most amount of votes in that round one. So under the plurality system, which was being used previously, he would have won. But of course, he doesn't have a majority. And so this triggered looking at the round two. And so when the votes are transferred from the third party candidates, we see that the Democratic candidate manages to squeak by with 50.62% of the vote. And so he won. So there are some interesting bits of what come from looking at this data. So we see that 296,077 ballots were cast. During this, 26% of the voters submitted a complete ranking of the 4 candidates on the ballot. However, 50.4% marked only a single candidate. So what happened was that even though we were using instant runoff, half of the voters reverted back to plurality. And so it's worth noting that this is not unique to Maine, and there's literature that describes other locations and situations in which this incomplete ballot happens. And so we see that informational barriers are kind of inherent in voting methods like ranked choice voting. And I think we can kind of tackle this along 2 different perspectives. One being on the information about candidates. So instead of just picking one and having that favorite or deciding who you wanted to vote for, now there needs to be enough research and deliberation between all the candidates in order to create a ranking. And maybe that ranking is really hard to create. So that's one dimension. And the other dimension is the process, right? So for instance, in this situation with Maine, this was the first time that they used this in a congressional election. So the ballots would look different. There's a lot of new ideas to get used to. It's worth noting that in a lot of instant runoff elections, they put a cap on how many candidates you can vote for. So there's a certain amount of strategy of figuring out how not to get your ballots exhausted. And so there's a lot of things to think about. But either way, ranked choice voting is, the proponents of it talk about the how it's more representative. It gives members more choice. It doesn't keep you in necessarily like the 2-party system we're so used to in the US. And it does work a lot better than plurality in trying to provide a majority. And so what we were really interested in studying that summer was if we can find a potential solution to these informational barriers that come from instant runoff voting. And so we wanted to propose random sample voting. And so the whole idea behind this is that by minimizing the informational barriers, we could minimize the amount of people who need to possess that information. And so we'll say that random sample voting is when we take a small subset of the voting eligible population, and they are randomly selected to participate in that election, and the outcome from that random sample is used. And this can be paired with any voting method we want. So you can do this with plurality, instant runoff, word count, whatever. And the whole idea is that hopefully we would be able to better allocate resources to said small random sample to give them like the education that they need to make informed decisions and maybe even work through deliberative processes. So as John said earlier, this talk or this work definitely focused more on the simulation aspects. And so we made a simulation that we would feed it a bunch of information and it would tell us a minimum sample size. So that's something that might be your next natural question, like, okay, so if this were to work, what would the sample size you need look like? And I just want to make a disclaimer right now, and the rest of this talk is not saying that we need to adopt random sample voting now. I think this is just a really interesting way in which we can continue to explore voting methods in different areas and in different perspectives. And this was a great undergrad project for me. And who knows, maybe there is some situation in some place that might warrant this use. Okay, so to answer the question of how large this random sample should be, the answer is probably smaller than you would expect. And so this is a distribution of minimum sample sizes. We're looking at 95% accuracy. And the way we're defining accuracy in this situation is that the result from the random sample matches the result if the whole population were to vote. So we looked at 2,000 elections with 3 candidates. And so we see something really interesting that in almost 50% of these 2,000 elections, less than 100 voters would do the job in getting you that 95% accuracy. And if we look that just under 80, that around here, right, we don't need much more for our I'm sorry. So for under only 1,000 voters are needed for around 80%. So this is a lot smaller than we would think. But so a next question that one might ask is why does one size not fit all, right? Why do we see such variation amongst these 2,000 elections? And so the answer is pretty intuitive and something you might guess, and that is that there is a very strong relationship between closeness of an election and the sample sizes that you need. And so here, the closeness measure we're looking at, we had a lot of different closeness measures that we engaged with, but this one is what we're calling ranked choice voting final round margin. And so we're saying that at the very end of the very final round of the ranked choice vote, we're looking at the margin between the 2 candidates and seeing the 2 remaining candidates and seeing how small or big that is comparatively. And so here we see a very strong relationship between our closeness measure and our sample size. And our R-squared is 0.9962, which is kind of flabbergasting to me. And it's even crazier that the 12 points we see plotted here are all from real election results. So these are 12 elections from data we got from the American Psychological Association. And so again, this is with 3 candidates and 95% accuracy. So this is just another way that we were able to explore this problem. Random sample voting did not have really any research beforehand. The research done before was more on a security aspect and like logistics and not a mathematical analysis. And so this was just another way in which we can explore how something like this could mathematically be plausible. So I want to turn back to Maine for a second. So if we remember our 2018 second congressional district election, we had a close election, right? The ranked choice voting final round margin was 1.24%. So our algorithm determined that the median minimum sample size needed for 95% accuracy was 16,881 voters. That's approximately 5.7% of all those ballots. If we wanted to look at 99% accuracy, that percentage goes up to around 11% of voters need to vote for this. And so this is just really interesting because we can see how even in close real world elections, our simulations demonstrate that this can be plausible. Now, I want to just highlight something because the assumption that we made in our simulations was that the voters inside and outside the sample were able to complete full ballots. But we know that's not necessarily the case in the real world, as we saw. And our whole motivation for looking at this problem in the first place was that hopefully that our random sample would be small to allow for the education that would give us the full ballots. So the question then becomes, can random sample voting with ranked choice voting be better? And by that, I mean, does a small randomly selected subset of educated voters who fill out complete ballots provide a better result than if a larger population were to vote where some non-trivial percentage would only rank one candidate? And so there's a lot of data here, so I'll walk us through it. But what I mean by better, and I'll just say this now. So for this first table, we have how likely RSV will be better if the outcomes of the sample and population don't match. By better, we're saying, okay, if we get two different winners from the election, from the random sample and the population using whichever percentage, then we're going to take those two voters and they're going to do a head-to-head contest. And the better would be the winner of that head-to-head contest. Okay, so we see we're looking at 100 and 250 and 500 and 1,000 sample sizes. And this is the percentage of the population we're choosing to vote only their first choice. So 0 to 10% means most people are really filling out their full ballot. 50 to 6%, or at least one vote. 50 to 6% is a half, and plurality would be 100% of the people only voting for their first candidate. So we know that with 1,000 sample size, we see that in our simulations, 50 and 60% of the larger population only voting for their first candidate, that there's a 58.26% chance that random sample voting would do better. And if we remember, Maine falls right in this region. 50.4% of the population of Maine only voted for their first candidate. And we saw that our random sample needed for a given amount of accuracy would be over 1,000. We notice for plurality, though, if we're comparing a random subset who vote fully and a population who just votes with plurality, that as small as 250 subsets, we'll see that RSV does better. And so how often, though, you might ask that there's a difference between what our population and random sample voting does, well, we see that even with as small as 100 sample sizes, it's at least 80% of the time that we see the same result. But we notice that as our population size gets, as our sample size gets bigger, the risk that your random sample will do worse decreases drastically. And the possibility that it might do better goes up. And so this is just a really interesting way in which we can further look at new areas of voting and kind of see how we can combine and alter methods previously used before. And so I think this work also really points out the need of educated voters. And so it's really cool to see all this work being done with as young as middle school students to get politically and mathematically literate future voters out there. So I just want to say thank you so much. I'm pretty sure I'm out of time. This is just a picture of me with John and Caitlin at MathFest, and feel free to reach out to me at rroca01 at Manhattan College, at manhattan.edu for any questions you may have if you want to chat. Thank you.
Thank you so much, Rachel. That was a beautiful and really sophisticated talk. Thank you so much for sharing that with us. Really enjoyed it. Are there any questions? Go ahead, Beth.
Rachel, I agree. Thanks. That was a great talk and interesting. And I'm especially curious about how you found the data. You mentioned that there was a lawsuit for that 2018 election in Maine. And as a result, they published full information about the ballots. Because it's sometimes hard to find, as you mentioned too, right? Sometimes hard to find all the information that you could dig into for examples or to try to consider different possibilities. Was it published through the Secretary of State's office or through Maine's state offices, or was it published separately? Do you remember, as a result of the lawsuit?
It was, I don't remember which office it was, but it was on like some section of the maine.gov website. So it was very easy to navigate to, and I'm happy to provide you I can send you links. I can dig those up easily. But
Sure.
so one thing to note is that this was very, very raw data. And so I spent at least a few days just writing code that would appropriately work through all this data. There were a lot of undervotes and overvotes. So where people would mark or voters would mark more than one candidate for a ranking, or they would just leave things blank. And so I had to write a code that incorporated the procedures, which was also publicly available on the website, in order to properly go through the data and discard the ones that Maine would discard for being invalid. So that was a process. It was like, there were, I believe, 7 Excel spreadsheets, and the biggest ones had 100,000 columns.
Wow.
Sorry, 100,000 rows and like 8 or 9 columns. So it was a endeavor.
A process for sure. Well, there's some great tie-ins there to data science too, and how to clean the data and all of that sort of stuff too, that could be really interesting to talk about with students. Thank you.
Thank you.
Are there any other questions? Rachel, maybe you can just tell us in a minute that we have, like, what your graduate program will be about.
Yeah, so I'm excited. I'm hoping it's going to mix everything together. So I'm a math person, but I'm really interested in data science. I do work in machine learning right now. And so I'll be working, I would love to keep working on work with math and social sciences. And I have a few advisors. They match you when you're going in, just to have someone to start out with. It's not mandatory, but I'm matched with a topological data analyst and a physicist doing machine learning and education. So I think it'll be a really cool way to kind of mesh everything together. So I'm excited.
It says one of our graduates, Katie Kinnaird, is now a professor at Smith College. She is head of an organization for women and machine learning. So if you're interested in being in touch with her or finding more about women in machine learning, let me know and I'll put you in contact. Okay. So thank you again. Let's everybody give Rachel one last applause, and we will break for 2 minutes and come back with our third speaker.